Recording. Now I'm recording. Yeah, good. Okay, we'll just zip through these. I don't think you're going to have the second test. I think is a lot harder than the first test.
Yeah.
But we'll look at it here.
The first one?
I think the second one.
Oh yeah, yeah.
This is the first one.
Yeah, the first one.
This is a non-graphic. So let's take a peek at these, and you just tell me now if we've got y equals 54 minus 6x squared sine x. We want to differentiate. We can take it. I mean, this isn't bad practice. Let's take a quick look at that. If I want to find dy dx, I've got two terms there. But whenever we differentiate multiple terms, we just differentiate term by term. Derivative of 54 is 0. Okay? So all we got to deal with is the derivative of the second part. Now, talk me through it. Okay, but I don't think we want to jump. Yeah, it's going to be a product rule. Now, it's really easy to just start jumping in.
Whenever you're ready.
In math and physics, I think, you start getting into really analytical stuff like this, in calculus and physics. It's really easy to jump the gun on problems. It's almost always worth your while, especially on tests, to not try to go too fast. You want to take your time and digest it, look at it first, get an idea. In the long run, it saves you a bunch of time. Don't just jump in and start working. Just take a second and say, okay, now what am I doing here? What's my strategy? Then jump in. Yes? Yeah. Oh, that's not even supposed to be there. It's just, when I copied it, it was, I'll do this. There we go. Now it looks better. Okay, so what do? If I'm going to calculate y prime here, product rule, what about that negative 6? It might seem like a minor thing, but it's a good idea to
just take it out.
Leave it out front. Pull the constant out front and leave it there. And then I'll do the calculus in the brackets. Right?
That's a constant?
Yeah. The negative 6. Anytime I've got a constant out in front, and the rule that would tell you that is, if we had to write one down, it would be this. It would be the constant multiple rule. I don't even think it's in the book. It might be, but here it is. The derivative with respect to x of c times, now we're going to start saying u instead of x, because now that we've got the chain rule, we're able to treat derivatives of functions of x instead of just plain old x, right? This,
It's a CU one.
so right, exactly. So what this is going to be is that answer, cu prime, where u prime is just du dx. Notice that constant is just stuck out front. It doesn't do anything. We can effectively pull that out of the derivative and not worry about it. Just multiply it through at the end. Okay?
Calm down.
So then, now we've got to differentiate this product. So how's that go?
First times the 0.
Okay, I could do 2x, the derivative of the first. That's fine. We'll do. I usually like to do, just so we're consistent. You're doing it right, but I like to do the first factor times the derivative of the second plus. So what's the derivative of sine? This is how I've been doing it. Cosine x plus, and that's important, that it's plus, not minus.
2x.
Sine x times 2x, right? And then I could just factor out an x, I guess, if I want to, or I could even redistribute the negative 6 if you want. It's not that, it doesn't help you that much to factor that one. Eventually we're going to want all this factor stuff.
Wait, was the 54 just turned to 0?
Yeah. Yeah, the derivative of a constant is 0. Okay? Make sense? Okay, next.
Wait, so that would just be your answer?
Yeah, or we could factor out an x if we want to.
I don't get why the -6 doesn't change. Oh, wait, yeah, I do. Never mind.
Okay.
I understand.
Yeah. So now maybe we don't want to leave it exactly like that. Let's go one more small step. What if I pull an x out? So I get -6x times x cosine x plus 2 sine x. Okay. We want to put the 2 in front of the trig function. Okay.
That's how you plug it in the computer.
That's how I would plug it in, yeah. I don't think on this one they would, I don't imagine that you would be marked wrong if you just distributed that -6x and wrote it as 2 terms either. I'm sure that would be fine. You see the difference between one like that though and one like that? I mean, there's a big difference. Look where we went. That's pretty ugly compared to, that's not so bad. I mean, that really did get simplified a lot, right? Yeah. Oops. Okay, quotient rule.
Yeah.
Right, straight quotient rule. We probably okay with that?
Yeah.
Okay. I mean, that's no big deal. There's no, yeah, there's differentiate term by term, so I'm just going to get 5 minus 9 cosine x. Does that make sense?
Yeah.
Derivative of x is 1, so I just get a 5. Derivative of cosine x is negative sine x, so a negative 9 sine x. Okay. These are a lot easier than the ones we did yesterday. Okay, how about a second derivative? That's probably one worth going through. So we'll just do that on here. So if I've got, oh yeah, we did. We did this one, didn't we? We did cosine. We did a harder one.
Yeah, we did.
I wasn't here.
Okay, let's do this.
And that's why we got the handout, yeah.
Yeah. So y equals 5 secant x. We're going to take a second derivative. What's the first derivative? Good. Derivative of secant x is just positive, secant x tangent x. So we're going to get 5, and then this part. Whoops. Won't do that. I'm probably going to get fired for that. It's been recorded, too. Secant x. Tangent x. Okay. What's that?
My text.
It's recording, yeah. So I hope your next teacher, you like
Post it
him.
to your YouTube.
Oh, yeah, I was
some of the recordings and I could hear Shane.
Okay, now what? If we want to take another derivative, this layer gets a little harder. How come?
You gotta take the derivative of, oh, you gotta do the
Power.
power
Or,
rule.
God.
Not power.
Product.
Product. There you
I
go.
would say power.
You screwed me up, Tanner. This is my brain.
Okay, so
It's just the derivative.
the derivative of a product of secant and tangent. Talk me through that.
Secant x tangent x.
Okay, secant x times the derivative of tangent x, which is what? Secant squared x. Good. Hey. Plus the second factor, tangent x times what's the derivative of secant x? Well, we did that one. Secant x, tangent x, and then we'll just close the quantity. And we got it. Now we could factor some stuff though. What could we factor out of both of those?
Secant x.
Secant x, yeah. Okay. And so we get 5 secant x times secant squared x plus tangent squared x. Okay, what we got? Okay, make sense?
I think I'm ready to pass these tests.
I think you are. Okay, find all values of x for which the function below is differentiable. Now, this is probably one worth looking at. Not that the calculus is so hard here, but the pre-calculus stuff might be a little tricky. Okay, so how could we do this one? We want to find we're trying to find all the places, what are we doing again? Where the function is differentiable, which is probably easier to do instead. Find the places where it's not differentiable, because those are going to be fewer. So where would that not be differentiable? 3.
Like what qualities the graph make it? Negative numbers.
Okay, and why are you saying maybe? How come -4 maybe?
Because it's jumping.
Okay, because it's jumping. But there's two things that could be going on there. If we look at the graph of the function, it could be doing, maybe it's just doing this. So you got -4, +3. So maybe it's just doing this. Maybe it's going, see? And that would be okay. If the function, now, what you got to think about here, how is that different from, say, that? Okay, that's a cusp for a sharp corner. That's not. Okay, they're both places where we're changing pieces of piecewise function. But one of them's different than the other. Now, how could we distinguish mathematically, without graphing it, how could we distinguish that case from that case?
Can't you get a derivative?
Ah,
No derivatives.
there you go. Because what's really going on here is the ant's evolved slope sense is going to say, okay, I'm feeling a slope of 0, slope of 0, slope of 0. It's gradually going to change. Up here, the ant's slope sense is saying, it's getting more positive, yikes, it's negative instantaneously, something's wacky there. Because then at this one point right here, he doesn't know what's going on. He can't define a slope there. Is it the slope that he inherits when he walks from the left, or the slope he inherits when he walks from the right? Whenever you're asked a question like that in math or in physics, you can appeal to the isotropy, is what we'd say, of the situation, meaning there shouldn't be a preferred direction. Everything should be on equal footing. Right? In space, for example, there shouldn't be, space is isotropic. It shouldn't matter how I'm facing, physics should be the same. It shouldn't matter which direction I'm walking from on this curve for things to be the same.
So what's that?
So when
line?
faced with a decision, our standard answer in calculus is, we can't define it. Whatever we're talking about can't exist there. Does that make sense? I said that might have been a little confusing, but you get the concept there? Yep.
What's the line between gradual and a cusp then?
Okay, so the line between gradual and a cusp, or a sharp corner, is just that if there's any difference between the slope as I approach from the left and the slope as I approach from the right, we consider that to be a sharp corner, even if it's a very slight difference and it doesn't seem like a very sharp corner. It has to be the same answer approaching from the left and the right in order for there to be no sharp corner. In other words, as the ant approaches this value right here from the right, the slope that he would anticipate would be the very same slope that he has when he's approaching from the right.
Because it's decreasing. Is the
Right.
Okay.
In other words, the tangent to this curvy curve would have to match up with that line right there. Does that make sense? Okay. So now how can we do that mathematically? There are some hard ways and easy ways to do this. But there's a really good, easy way to do this. You guys are going to get it too. Here's my function. How could I know what the ant's slope sensor is sensing at -4 for this function and that function? Yeah, differentiate. Take the derivatives and see, right? Let's take this piecewise function and just differentiate. Okay, so we'll get something like this. If this is y, then isn't y prime just equal to, when x is less than or equal to -4, what is it? What's the derivative of the quantity x plus 5 squared? Now I've got a power, right? So 2 times the quantity x plus 5. And then what's the derivative of x plus 5? 1. So it's just 2 times the quantity x plus 5 to the 1, right? Times 1 if you won't even write. Okay? Now what about down here? When, and I honestly shouldn't even probably, I'm not going to. I'm going to erase this for a second. We'll just get rid of this part. Because we can't presume things that we don't know to be true yet. We'll just do the derivative parts first. So the derivative of x plus 5 is 1. Okay, and the derivative of the quantity 4 minus x squared. See if you can do this one in your head and simplify it for me. This is good practice. There's 2 steps to it. See if you can do the 2 steps in the chain rule and then combine it into a nice answer for me. What do you think? If I differentiate this bottom piece, the piecewise function. Okay, negative 2 times the quantity 4 minus x. See how we get that? We're going to bring the 2 down in front by the power rule. So we're going to get 2 times the quantity 4 minus x times the derivative of 4 minus x, which is negative 1, right? And so the negative gets grouped out with the 2. So everybody see that? So it ends up being negative 2 times 4 minus x. That's really, honestly, that's good to do. Just as a kind of a skill building thing, the equivalent to when you're in sports, just to working on a repetitive skill. Doing algebra in your head makes your brain tougher.
Do that on top?
Because because the derivative of the inside was positive 1.
Oh, so we only do the chain rule when they're negative?
No, you did the chain rule, but it was just 1, so when you put 1 times that, it's just that.
2.
The chain rule says...
See, there's the chain rule for the top one. Right? Now for the bottom one, see what I'm doing? For the bottom one here, it's 2 times 4 minus x to the 1 times minus 1. See, so we just combined it into one answer. Okay? All right, so now we can see what's going on. Well, so if we want to know, for example, let's use this model here to, I want you to tell me what is f prime of 5. Okay, so where is, when x is 5, we're walking on which part of the function, top, middle, or bottom? When x is positive 5. Bottom, right? X would be greater than or equal to 3. 5 is greater than or equal to 3. So f prime of 5 would just be negative 2 times 4 minus 5, right? Does that make sense?
How would you know to automatically pick 5?
I just made it up.
Well, why?
Well, I'm just giving you an example. I'm showing you for no reason. I'm just saying we can evaluate the derivative of this function now wherever we want to. Where we're going to want to evaluate it is at 3 and negative 4. Those are the important places. But if we were to evaluate it at 5, we're just going to evaluate this derivative, the piece of the derivative that makes sense when x is 5. When x is 5, we're on the bottom piece of the function, right? So if I want to evaluate the derivative, y prime at x equals 5 is just 2 times the quantity, negative 2 times the quantity 4 minus 5. And so I get an answer of positive 2. So all that would be telling me then is at x equals 5, the slope of the tangent is positive 2, right? If I plug in 0, real quick, you just tell me, what's the derivative of this piecewise function when x is 0? 1, sure. Because that x equals 0 puts me in the domain of the middle part of the function. And the derivative there is 1 and constant, right? Okay, but what we want to do is we want to see if where we join up, the derivatives are the same. Okay?
So you're basically just kind of guessing and checking or not.
Well, no.
Guessing.
Now we're not going to. I was just giving you examples of showing you. All I meant to do there. Everybody, really focus on this. Focus. You got to. This is the part that your brain should. No pain, no brain gain on this one. It's a lot of rhyming. When we evaluate a piecewise function, going back to Algebra 2 and even last year, first thing we always have to do is figure out, well, which of the pieces are we plugging in for, right? Depending on the value of x that we pick. Well, same thing is true with the derivative. All we're doing by taking a derivative here is we're trying to find out what the slopes are of these three pieces, right? That's all we're doing. That's what the derivative does, is it tells us the slope of the function for any value of x that we choose. Okay? We want to see what's going on where we join, though. Is it going to be a sharp corner, or is it going to be a nice smooth transition where the derivative is defined? So we'll take a limit. We'll do this. We'll find what is the limit of the derivative as x approaches, let's do -4, as x approaches -4 from the left, from values less than -4, right? Well, for values less than -4, we're on this part right here, right? So if I'm taking the limit of 2 times the quantity x plus 5 as x approaches -4 from the left. And if I plug -4 in, don't I just get 2 for my answer? Right? So all we've said then is, as we have, I wonder if we should look at a
Go
graph.
over that
of
one
this.
more time. I didn't understand.
Okay, let me say that again. And there's one more way. There's another way I'm going to go through this that will link what we're doing now and put it all together, and you'll have it for sure. We want to know. We want to answer the question as the ant is approaching. And I erased my graph, didn't I? Yeah. Okay, go ahead. As the ant is approaching this break in the function, he's going to shift gears from this function to this function. We want to know what is his slope sensor reading when he's walking from the left towards this junction, right? So if we want to know what's going on then, we want to just take the limit of his slope as x is approaching -4 from the left. So he's in that domain, right? So all I'm going to do, well, here's the derivative, right? There's the derivative that we're going to evaluate directly. So we're going to plug in 4 minus for x, or -4 minus, sorry, right? As he approaches -4 from the left, x is going to approach -4. So I'm going to plug that in, right? And I'm going to get 2 times the quantity -4 plus 5, which is just 2 times 1. Okay, so what he's seeing then, as he approaches a value of x equals -4 from the left, that's his slope sensor reading, +2. Okay? Now, what if he approaches from the right? Let me get rid of all this stuff down here. That's jumbling stuff up. I'm feeling. I got too much garbage up here. Now let's look from the right. The limit. Whoops. The limit of y prime as x approaches 4 from the right. Well, approaching 4 from the right means I'm in there. -4 from the right. Agreed? This is the middle function is where the ant is walking when x is greater than -4. So approaching -4 from values bigger than -4. We're just taking the limit of this y prime. Well, the limit of 1 is always 1 regardless of what x value, right? So I get an answer of 1. So if the ant's slope sensor, as he's walking towards x equals -4 from the left, is reading 2, as he's approaching -4 from the right, it's reading 1. Those are different slopes. So I've got something like this going on, right? that kind of a thing. I get a different slope from the left than from the right. And so, is the derivative defined there? No, it's not. Okay. Now, okay, right? What about the bottom one then? You walk me through the bottom one. If I want to know if he is sensing the same slopes from the left and the right at the other transition at 3, what's that going to look like? Oh, shoot.
Yeah. So did you take the limit of -2 times the quantity of 4 minus x as x approaches 3 on both sides?
Yeah. Okay, so I want you to tell me then, what is the slope sensor going to say? What's the limit of the derivative function as x approaches 3? That's the other boundary. From the left, let's say. Okay, that's taking the limit of what function? What derivative function? Where is x?
Negative. Wait.
Where is x slightly less than 3? Top, middle, or bottom?
Middle.
Middle. Okay.
Okay.
So we're taking the derivative of the middle. We did that. The answer was 1. Right? So y prime in the middle piece was 1. As x approaches 3 from the left, what's the limit of 1? 1. Sure. Okay. So the slope sensor at the second boundary, as we're approaching from the left, he's sensing a slope of 1.
Now we do it from the other.
Now I get to take it from the other side. Okay, so the limit of y prime as x approaches positive 3 from the right. Now, if I'm approaching 3 from values bigger than 3, I'm walking on the bottom piece, right?
Yeah.
Okay? So that's going to give me the limit of -2 times the quantity 4 minus x.
X approaches 3 from
Well, if I plug 3 in there, I'm getting -2 times 1, -2.
So that's a cusp 2.
So that's also a cusp. You see why?
Yeah.
Okay, now here's the kicker though. What if those had all worked out? So the ant's slope sensors had been equal on both sides. Does that mean that those derivatives exist? Because there's one other thing that we still have to consider. We probably should have considered it first, but I wanted to talk about this stuff. What about the original function? How could the slopes, can somebody draw me a picture, a double dog dare to draw me a picture where the slope sensors would read the same from both sides, but the derivative would still not exist? Yan Yan's got it. What do you think? You want to do it? Okay, a hole in the function would work. Yeah, that's one possibility. Sure. That's something. I'll buy that.
I'll buy that.
What? Okay, so here's one way. If I've got a function that's doing this,
Oh, yeah.
something like that, even if the slopes are the same from both sides, that wouldn't work. Now, that's not going on here, though. That's not going on because we've got all our bases covered. Look, we're at the transition points of x equals 3 and 4, there's always one piece of the function that includes that x value. So we've got no holes in this thing, but there's something else that could happen.
Oscillation.
I know.
Think you know it?
Doesn't it look like it goes straight and then crosses through the middle and then to the right?
Well, come draw it. Come draw it.
Grab me dry erase marker. It doesn't have any situation that. I can use this one, right?
Mike.
That?
Not what I'm thinking. No, not exactly. I'm not.
Do oscillating one.
Maybe I'm missing something. What were you thinking?
Kind of draw oscillating one.
Why? So you can't take derivatives of.
Oh, where it's vertical.
Yeah.
Okay. Yeah, okay, that could be, but that's not what's happening here either, though. We can see in our function, if we took the time, we can see in our function that nowhere is this function. These are all just either parabolas or lines, and so it's never going to be vertical, but there's something else. Now let me say the question again. Can you draw me a sketch of a curve where an ant could be approaching a value from the left. And let's make the value. Let's say the value is just arbitrarily going to be, is going to be 2. So where the ant is approaching a value of 2. So when he's crossing this imaginary vertical line, when he makes the transition, how could he sense the same slope from the left and the right and still not have a derivative there?
Is it an oscillation?
How about this? Do you agree? Do you agree?
I like it.
The ant approaching from the left is seeing, in this case, if I, assuming my drawing is not terrible, is seeing a slope of 0. From the right, he's witnessing a slope of 0, experiencing a slope of 0, but there's a discontinuity in the function. Where there's a discontinuity, the derivative can't be defined. Does that make sense?
Yeah.
Okay.
This is a jumping.
So it gets now. Just to make it, did I expect you to know all that? Not really, because on the test, what you could have done on this one, theirs is not this hard. All you had to do on this one, if I were to plug in -4 for x there, and hang on. Well, look what happens here. If I plug in x equals -4, I'm going to get 1 squared is 1. And I get 1 there. So these two do match up. So here's one where I guess I didn't think they were going to do this to you. But here's one where
You would have to.
the function is continuous, but because the derivatives don't match up, it's a cusp. What about down here? If I plug in 3, I'm going to get 2. If I plug in 3 here, I'm going to get 4 minus 3 is 1 squared. So the values of x or y don't even match up here, right? As the ant approaches x equals 3, on this function, he's approaching a y value of 2, and down here he's approaching a y value of 1. So there's a broken function there anyway. Say it again.
Can you go back to the question?
Oh, yeah.
I forgot what that was.
Okay. Find the values of x for which the function below is differentiable. So it would
All
be
fields are except negative.
that one. Right? Yeah, here, come on, I'll show you. All that means.
Wait, can you delete a couple of my attempts on the test?
Yes, I can.